Hello?
Yeah,
Good. So hi everyone. My name is Guillaume Cuiron. I have the pleasure to chair this session, which is going to be on using large language models for planning. So we have the pleasure of having Subarao for this talk. You can ask your questions online. Otherwise, there's going to be a Q&A session at the end of the talk. So Subarao, the floor is yours.
thank you. Okay, so you can hear me, I hope. Can you just give me that in case I need to use it? I'll just keep it here. Just want to try this, yeah. So I am Rao Kampapati, and I am going to be talking today about the role of large language models in planning. I guess a lot of you are probably here both because the word LLM is there and because the agentic LLMs have become like the great hype word of the current month. So we'll talk about what would be the possible things that LLMs can do for planning. Okay, I do have the tutorial slides available there. I tweeted them. There's also a QR code, and I also put them on the tutorial page on Open on the ICML thing. Okay, so there is an actual overview of the tutorial, but obviously there's a part 1, there's a part 2, there's a part 3, there's a part 4, but it makes a lot more sense once I start. So basically, let's start with the part 1, which is the introduction to the tutorial to some extent. By the way, I noticed that there is a bunch of live translation, live speech recognition going on. Try to ignore that because AI hasn't yet come to the point where it actually understands what I am saying. Humans are still much better at my pronunciation than AI has been. Okay, so the aim of the tutorial today basically is this, that there's been a significant rise in interest in using LLMs for planning tasks, particularly because of the whole agentic LLMs sorts of ideas, and also whether LLMs can do reasoning and planning. Even though actually I'll be talking a lot more about planning, planning is a form of reasoning, and so many of the things I say would be relevant to reasoning too. So that's what's saying that. So in the last 3 years, many papers have been published saying LLMs are zero-shot XXX, where XXX is planning, reasoning, whatever you want to think about. And both with empty transformers and also pre-trained LLMs, where pre-trained LLMs have trained on the web scale corpora. We focus in this tutorial on the pre-trained LLMs, the SOTA LLMs, state-of-the-art LLMs, and what they can and cannot do. So now the interesting thing is that much of the literature on whether LLMs are doing planning has been in NLP and machine learning conferences. And yet the planning folks essentially tend to go to somewhat different conferences, including ICML, but also ICAPS and constraint programming, et cetera, et cetera. So there's been a bit of a bidirectional ignorance because people are discovering what planning is from the machine learning side, and people in planning are rolling their eyes saying, what the heck are you guys doing? I think part of the reason I'm taking the time to do this tutorial is to rectify this ignorance and take a critical look at the role of LLMs in planning. This is not going to be a hype tutorial. It would be a balanced one. It says there are certain things they can't do. It'll also say that they're very useful for doing certain other things. That's what we're going to be doing. That's the aim of the tutorial. Okay, so who am I? I basically am coming, I've been in AI for like forever. I tell my friends that I was doing AI way before it was cool. I wasn't there in 1956. I was born a little later than that. But I've been working in planning and scheduling and a bunch of other things. So I've done a significant amount of work in automated planning in terms of different kinds of planning scenarios, system dynamics, different kinds of optimization metric, different levels of completeness of the model that the planner has access to when it is doing planning. So all of this is, and by the way, I will be saying in a minute, but this community tends to think about reinforcement learning. Planning is a sequentialization problem. Reinforcement learning essentially is planning plus learning. So the model that the agent is using, it's also trying to learn on the side. So we'll talk about it in a minute. So there's a bunch of connections to RL2. Okay. So, and then I've also done in the last 10 years or so a significant amount of work in explainable AI and human AI interaction. That's not directly related to this particular tutorial, but in case you're interested in this, a bunch of stuff on that sort of a thing. Coming to this particular tutorial, I need to sort of establish my, bona fides, partly because this is my second ever ICML. I went to Hawaii ICML because it's in Hawaii, and I'm coming here because it's in Vienna. But I have been doing a bunch of work in the planning capabilities. When I say I, when an old professor says I, he or she really means their students. I will show you the pictures of them really, but they have been doing great work on understanding the limitations as well as capabilities of large language models in planning. There's actually going to be a position paper tomorrow. It's a spotlight position paper tomorrow at 1:30. So actually this is a elaborated version of that position as well as literature review and so on. So that's going to be at 1:30 tomorrow. So you can even use that as a Q&A session in case you haven't gotten enough questions today. Okay. So what am I going to say about LLMs and planning? Well, there's red and there's green. Okay, the red part is LLMs actually cannot plan according to what I will tell you about. The full planning problem involves reasoning and combinatorial reasoning that LLMs are basically incapable of doing. So they can't do planning in autonomous modes. Chain of thought, react, fine-tuning, etc. don't help that much. They cannot improve by self-verification. Lots of people would love to say that maybe LLMs can't right away get the correct plan, but then maybe they can self-verify. Well, honestly, it turns out that if they try to self-verify themselves, their performance goes down. And my suggestion to any of you who are trying to solve a problem that you don't understand is go with your gut instinct and don't try to correct yourself because you don't know what you're talking about, so you're likely to make more mistakes if you try to correct yourself. So it turns out actually there are papers on that. I'll show you, talk about that. And having humans iteratively prompt is actually an invitation for clever hands effect. I hope I'm in the German speaking world, right? And how many of you know clever hands? The great horse. Okay, so clever hands essentially was this really smart horse that was doing arithmetic, and it turned out that what it was doing was not arithmetic, it was just essentially sensing the tension level of its owner. So if you say 9 + 4 and it starts stomping its hoofs, and when it comes close enough to 14, the owner will start panicking and the horse can sense and stop stomping. That's basically what it was doing. And it turns out that there's a bunch of clever hands effect that goes on when people tend to be in the loop and keep giving credit to LLMs. One of the funnier, interesting parts, by the way, is normally we are not at all happy about giving credit to anybody else. If we solve the problem, we want to take the credit. But humans, the ICML, NeurIPS humans, would love to give credit to LLMs. Because if the LLMs get the credit, you get a paper. If you say, I solved it, you don't get a paper. Okay? So anyway, that's the red part. And actually, that's like a big part of the tutorial. I want you to understand why this actually makes sense because you don't see this viewpoint expressed enough. And as I said, I'm not coming out of nowhere. We have referred papers, etc. on this. So that's one thing. And then the second part is that the fact that LLMs cannot do planning by themselves doesn't mean that they're useless for doing planning tasks. They actually are amazing idea generators. They can generate ideas about what a plan should be, ideas about what should be the specification of the problem in terms of how to improve its completeness. They can give you ideas about what the domain model itself is. There's a whole bunch of roles LLMs can play, but they cannot guarantee robustness of the plan that they generate. So we actually you have to use LLMs with verifiers in the loop, either the humans or automated verifiers in the loop. And these automated verifiers might actually be using models that themselves can actually be teased out in a semi-automated fashion from LLMs. There are papers on this, okay? So in the LLM Modular Framework, in this sort of a view, LLMs can play multiple roles. They can guess plans, guess domain models, help elaborate the problem specification, and of course, translate formats. Using LLMs to translate formats is a poor man's way of using LLMs, really, because they're just great for that, and you should want to use much more than that. Okay, so that's what is going to be the bigger message of the tutorial. I understand that at this point, I'm happy that not too many people already left right after that slide, because I have this worry that in the ICML 2024 tutorials, there are the LLMs are zero-shot XXX tutorials that are like a gazillion people. And then, the tutorials like mine, which say maybe they can't do some things, but they can be useful. And, there is going to be a worry that you might not actually be interested in hearing the nuanced part. So actually saying anything less than full-on hype mode about large language models is sort of like kicking a cute puppy. Nobody likes you if you kick cute puppies, right? So I want to bring the cute puppy or the elephant in the room up front and say, no, I'm not here to lament LLMs. I'm here to leverage them. And part of using any technology in the right way is to first understand what it is able to do and what it's not able to do. Okay, and both are important, and that's basically how science works. Okay, so a clear-eyed understanding of the strengths and limitations of technology is a step towards advancing it, and blind cheerleading or unallied cynicism, in contrast, are just steps towards advancing your influencer career. I don't have too many followers on the Twitter, so I don't have much of an influencer career, so I will just go with the science part. In general, I also want to point out that there's a CSM article there that AI in your time, and certainly in my research time, has gone on to become an ersatz natural science, where basically we are training these huge, large models and we have no actual clue what they do. We poke them and see what they do and try to write papers about them. This is what zoologists do. They go into Amazon jungles, find some funny animals, poke it and see what it does. The difference is we don't have very good empirical discipline. So we tend to actually make this observational claim sometimes without being adequately critical about what you're trying to say. And so that's somewhat of the reason why people tend to think that they can do things that this tutorial I will try to show you that they can't do. Okay, the other thing I want to say is that you all heard about alchemy, right? I think the point about alchemy is not that chemistry is a bad subject. Chemistry is an amazing subject, okay? What was problem with alchemy is that a bunch of bozos, including our own ancestors, thought that chemistry will become nuclear physics if you prompt it the right way. That is alchemy, and LLMs have the same problem. LLMs are actually quite amazing in what they can do as idea generators, and that with other reasoners and other humans in the loop can do much better than what we were able to do before. But on the other hand, they are not going to be able to solve every possible kind of thing, including reasoning and planning problems. The other part about the far side cartoon is actually quite relevant because LLMs are this very interesting beast. On one hand, we are saying that there are SOTA LLMs that can take million or 2 million token context windows, as if they understand all of that stuff. Okay, any of you heard of needle in the haystack? That's a silly way to check whether somebody has actually read an entire book. For humans, maybe it might be useful, but for a system like LLM, needle in the haystack doesn't at all guarantee that it actually understood what was written there in the entire context. So on one hand, we are saying million word context windows are there for LLMs, but on the other hand, every day you see papers showing that very small prompts, they misunderstand what they mean. In fact, we'll show that the planning problems in a minute will actually, the prompt is very short and yet it just dies because it's not really going to be reasoning. And part of the issue, I've always looked at this Far Side cartoon, and I felt sorry, not for the dog, but for the guy. Okay, so it's like you should know what LLMs can and cannot do, and hopefully that's part of what we are going to try to do. A few caveats about the tutorial. This is not a dry chronological survey with a laundry list of papers and their blurbs. It's an opinionated perspective on the state of LLMs and planning intersection, informed by, partly by my own work, my own group's work in this area. And I should caution that the authors of the papers brought up in the tutorial may well bristle at the particular perspective or pigeonholing of their work. But then they can give their tutorial tomorrow. That's completely fine, right? The point is, the aim is not to make up your mind about those papers, but to equip you with a perspective that you may find useful when you read the literature yourself or do the work in the area yourself. This is ICML. These are the people who are going to do the work. So I wound up giving these talks to general audience, but here I'm giving talks to people, a whole bunch of grad students who are going to do very relevant work in these areas, and I'm hoping to try and affect the way they look at the problem. I should also mention, as you can see from a bunch of tweets on the side, this tutorial has largely been tweeted because I've been thinking about these problems. In addition to writing papers, I also write on Twitter because I learned quite a bit from serious discussions on Twitter, so I do that myself to the extent possible. So this is also kind of a tutorial. Well, if I'm busy tweeting, who is actually writing papers? Those are the people who are writing the papers, okay? Those are some of my students, Karthik Valmikam in the front, then Mudit, and then Siddhant, and then Lin Guan, and Kaya with the proof, and Lucas Aldata, some of my current students. You'll be hearing about some of the papers that they've written relevant to this tutorial. Okay, so the perspective, so next two things, in the part one, I want to give you very quick perspective of my own, because I'm not going to give an LLM tutorial, there's a million of them going on, but I want you to look at it in a certain way so that things that I'm saying will make more sense to you, okay? And so I spent a bunch of time writing about these things, and so obviously LLMs are sort of n-gram models, except n-gram models on steroids. We know small n-gram models, but we now have even good old GPT 3.5 with a 3,000 gram model, and these million token ones are million gram models too, effectively. And so our intuitions about small n-gram models don't seem to necessarily work for very large n-gram models, but at the same time, they ultimately are n-gram models. The rest of maybe they will do something else is just hoping against hope. And of course, as this crowd already knows, the thing about LLMs is not how big the size, the number of parameters are, but how small the number of parameters are. Because if you actually try to remember the conditional probability tables for, let's say, a 3,000 word window, then with a 50,000 word vocabulary, then you will have 50,000 power 3,000 different predictions to make, and that number is really infinity. Okay, compared to that, 176 billion is just tiny and tiny. So there's a significant amount of compression that's going on during the training, and any compression corresponds to some kind of generalization, but it's not necessary that the compression led to the right generalization. And in fact, one of the most questionable issues in machine learning in my time observing the field has been the word generalization has almost been overused to the point that it has no meaning, honestly. So we will actually talk about it in a minute. Okay, and of course, you know that people tend to think of it as just nice big neural network, but it's like huge, gigantic, humongously large neural network trained on web scale corpora. And you guys think you know web because you check web, but really you don't. Okay, none of us know all the stuff that's on the web. And so there's a lot of misconceptions that would arise because LLM did something, and you think it just somehow emerged out of, de novo out of the LLM, but it could actually be explained also by sort of an approximate retrieval that I'll be mentioning in a minute. So N-gram models basically are always completing the prompt. And when they complete the prompt, the thing that they get out is not corresponding to anything that's been stored in the training data because it's an N-gram model. So essentially, they're always hallucinating. There's no actual guarantee that what they write down is actually correct. So I'd like to think of hallucination problem as LLMs always hallucinate. Sometimes their hallucination aligns with your reality. Okay, and this is a better way to think about what they're actually doing. And prompt engineering doesn't necessarily change this because whether or not changing the prompt gives the factual completion or correct plan depends on the prompter knowing enough to tell whether the given answer is accurate one. Sometimes it's possible, sometimes it's not. In fact, for search, for example, if you don't know the answer, why are you calling LLM? Because if you're calling LLM to check what it says and then go to Google to check whether the answer is correct, you're wasting your time, right? So it's worthwhile remembering that approximate retrieval always leads to hallucination. Hallucination is not sometimes, it's always. That's a better way to think about it. And I also want to mention that, retrieval in databases, which is given a query, given a key, retrieve the records that exactly match the query. The retrieval in information retrieval, where the key is approximately matched to the documents, but then the retrieved documents are actually present in the database, right? So Google never makes up a page until they added Gemini and started making up the pages now, okay? Approximate retrieval in LLMs is given a prompt, they're essentially generating a document using completion, and it's worthwhile remembering this, that's what they're doing. And this is both the boon and bane of LLMs, and you have to kind of keep that in mind. The one thing that I want you to understand is LLM's approximate retrieval upends our intuitions regarding computational difficulty of various problems and how LLMs solve it. In particular, computational complexity of the underlying task has no bearing on the LLM guesses. If you give as a prompt a question whose answer requires semi-decidable or undecidable computation, or a prompt whose correct answer requires polynomial or sublinear computation, do you think LLM is going to think a little bit more for the undecidable problem? No, it's actually just going to give the next token in constant time. And it's worthwhile remembering that. So underlying complexity of the problem has no impact on LLM's ability to guess the answer. But the problem is all our intuitions in computer science have been based on whether or not a problem is easy to solve depends on its computational complexity. And those intuitions clash with the reality of LLMs. For example, when people say LLMs can do self-verification, part of their intuitive motivation is that verification is oftentimes cheaper than generation. That's kind of true for most problems. But nobody ever said that LLMs are actually solving the problem. They are approximately retrieving answers, generating answers from the training data. And so specifically, the computational complexity does not make a difference, and you should keep that in mind. So it actually also means that the usual problem characteristics, such as stochasticity, partial observability, etc., which make either machine learning or planning algorithms go bonkers because they have a hard time dealing with them, are actually not going to have any effect on LLMs. They don't really care about what the computational complexity of the underlying problem is, as as encoded in the prompt. And this should not be surprising. You know this. That's the one part. The other part is the background knowledge, something that has always been a problem in AI systems, is actually easier for LLMs, approximately speaking, because Sam Altman spent all his money, or Satya Nadella's money, and trained the heck out with the entire web corpus of our collective conscience. Okay, and so to some extent, a whole bunch of things can be, LLMs can do approximate guesses on a whole bunch of things. And so they can provide common sense completions approximately, domain knowledge approximately, theory of mind approximately, analogies approximately. Okay, and of course, in addition to this, probably the most impressive thing for most of us, at least when you first use LLMs, is their linguistic abilities, such as summarization, elaboration, and in particular, format change. Although you have to remember that summarization is actually a reasoning problem. Most of the time when somebody gives you a summary, you say, "It looks good to me." Because I didn't have to read the whole book. You got me like one page. The right way to check whether the summary I gave you is the summary of the book is to read the book. Who the heck has time for reading the book? So I give you a summary, you will assume that I write. In fact, I'm going to give you summaries of various papers, and you just assume that, this poor guy is standing here, maybe he's right. If you actually know anything better, you should go and read those papers to check whether actually I'm telling you the right summary. Okay, so that's about LLMs. Perspective on planning. So LLMs part is actually more or less preaching to the choir, because all of you know more about LLMs than probably I do. But perspective on planning is something that might be useful for many of you. Let me put that out, because I'm going to tell you about LLMs and planning, and so you should know something about planning. So planning, scheduling, reinforcement learning, they're all connected. Basically, they're sequential decision problems. In the case of planning, given a set of objectives, we are interested in coming up with a course of actions or a policy, a plan or a policy to achieve them, hopefully with some guarantees such as optimality. Okay, standard planning problems as well as the reinforcement learning problems assume that the possible actions that the agent can take in coming up with this plan are given to it beforehand. So ultimately, all you're trying to do is figure out how to sequence the actions such that, or how to put them into a policy in the case of MDPs, such that you would actually achieve the specification, of the problem. So that's the standard planning or RL problem. There is this other type that typically we don't do in the technical AI, but we do in real life, is MacGyver planning problem. Are any of you are from India? It's what's called Jugaad planning, which is basically figuring out what are the actions such that this problem can be solved. So you're actually making up actions out of thin air so that the problem can be solved. So MacGyver planning in its full form is actually harder than planning. But sometimes you might be impressed enough that you came up with new kinds of actions and don't check about the correctness of the actual plan that happens. So the reason I bring up MacGyver planning is actually many times when people think LLMs can do planning, they're more impressed with the fact that it came up with an action that they didn't write anywhere. Okay, but it's there somewhere on the web, and it was able to actually put together some actions. But the question is not just whether you can think of actions, but whether the sequence of actions that you put together actually solves the problem. If you don't solve the problem, then you haven't solved the planning problem. Scheduling is a sub-case of planning, and in fact, many people who write papers on LLMs and planning in ICML and NeurIPS and iClear are actually doing scheduling problems. They just don't know the name. And what is scheduling? Scheduling is just given a set of tasks, jobs, and a choice of actions for accomplishing each of the tasks. Assign actions to tasks so that there is no undesired interactions. The job shop scheduling is one, where there's a bunch of jobs to be done. There's a bunch of machines. You're deciding which jobs are being done on which machines so that there is no contention between the machines. That's a scheduling problem. Planning, as I said, is more general than scheduling. So scheduling is kind of a special case. Not surprisingly, even in the simplest scenarios, such as what's called the strips planning problems, planning's computational complexity is p-space complete. I know that we no longer talk about computational complexity in the time of LLMs, who the heck cares, but they still exist. So they're p-space complete, whereas scheduling is only NP hard. Okay, so that's the way to remember that. Model-based reinforcement learning is basically connected to planning problem, where the agent is actually trying to learn the models of the actions that's been given. So in the case of planning, they give the actions as well as their models. That is what are the preconditions and effects. So which basically allows it to kind of know the transition function. In the case of RL, you are learning the transition function. You, the agent, are learning the transition function and using it to come up with a policy. So you're doing both at the same time. So the planning part of RL is still connected to normal planning problems. So this is just an example to show that you can start from scheduling, like job shop scheduling, and put more and more choices such that in the end you will get something like planning. In one of the important things about planning, and we kind of see this intuitively, is this notion of cascaded preconditions. You may just have one goal, right? How many of you seen this old movie called Do the Right Thing? Spike Lee's, okay? The life's goal is just do the right thing. So there should be an action which gives you did the right thing. But the damn thing is that that action will have a huge number of preconditions, and you have to work on those preconditions, and work on those preconditions, and work on those preconditions. That's what makes planning hard. So cascading preconditions is what makes planning hard. Scheduling normally doesn't have cascading preconditions of that indefinite length. One other thing I want you to think about, again, this is sort of intro to AI, but I do know, with all due respect, for those of you in grad school, that some of you haven't done intro to AI because you went directly to deep learning. And so it's kind of worth remembering a few things that you would have learned if you did those. Ergodicity, robustness, and quality and optimality of plans are worthwhile understanding. So an environment is ergodic if the agent can reach any state of the environment from any other state with positive probability. So as a corollary, in non-ergodic environments, an agent can get stuck in a state or a group of states and not be able to come out, because of which it won't actually reach the goal that you might be trying to reach, that you ask it to reach. Planning is most critical for non-ergodic environments. Remember that, okay? Because in an ergodic environment, you can blunder through. Do a couple of actions. Even if you fail, the world isn't going to end. You pick yourself up and do more actions until you reach a state where the goal is satisfied, okay? But if the world is non-ergodic, you may die. In fact, or your robot might get stuck. And so there is no much hope of coming out of this. Whole point of saying I can do planning is that your plan actually works. Anybody can give plans if they don't have to work. Okay, that's worthwhile remembering. Robustness of a plan is informally the probability that it achieves its objectives without failing or getting stuck. Okay, in deterministic environments, correctness is robustness. That means the plan is correct with respect to the model. In non-ergodic environments, you would like high degree of robustness. I understand you will never get 1.0 probability. I flew from India to here yesterday. There was no 1.0 probability that I would reach here. But neither did I say any random plan will work. I did my best to make sure that I'll actually be here when you guys are here. So you want to increase the robustness, okay? One of the things is top K correctness has become a big deal in LLMs. That if you ask LLM, it'll give you K different plans. Maybe one of those plans is correct. If you are in a non-ergodic environment, that's useless. Do you understand what I'm saying? Because if I give you two plans, only one of them works, you don't know which one works. If you do the wrong plan, you might die. So that's the whole point of non-ergodic environments. And in general, top K correctness, that is somehow you were able to generate one of the plans that is correct in the top K, where K is equal to 500 or 10,000, is not really of use for non-ergodic environments. For ergodic, it could be useful, okay? While robustness is a measure of correctness, quality of a plan is another thing that we tend to think about. Correctness is, did it reach the goal? quality is, are people, are the specifier of the problem happy with the way the goal was achieved? These are the sort of often unstated, common sense expectations about good plans. So for example, a way I could have come from India to here by walking 1 mile, running 1 mile, taking a bicycle for 1 mile, etc., etc. At some point of time, I'll reach here, and that would be a correct plan, but that will be a pretty bad plan from stylistic perspective because nobody considers that as a reasonable travel plan, even though it's correct. Okay. Now you can always convert style into correctness by putting constraints, saying your plan cannot take more than this much time. And that becomes, correctness. But oftentimes, style considerations are not spelled out. Okay? In general, both in RL and in planning, getting policies and plans that people will feel are good and reasonable has always been an issue because the style considerations are hard to capture. The interesting thing is LLMs are style masters. They are vibe machines. They actually will give you something that looks like a plan that people will like. It may not actually work. My joke is if you want a wedding plan, LLM will give you a wedding plan. But you would be a fool to actually get married with it. Because whether or not the plan works doesn't depend on whether or not it's high level, it looks good. It depends on whether the ring is at the right place at the right time, for example. So logistics actually matter. And you do need to consider that in terms of the correctness. But the style part of the things is actually LLMs are very good in giving you that information. So keep that in mind. The last thing on the planning part is world models, verifiers, and simulators. The way a planning agent approximately verifies that the course of actions it came up with is actually robust is by checking whether it is correct with respect to some model. This model might have been given externally, such as a PDDL model or a SAT modular theory models, or might have been given as a domain simulator. Many of you think domain simulators are different from models, but domain simulators are written by people. They don't fall from the trees. Okay, so they are actually knowledge that somebody has about the model of the domain that somebody wrote into the simulator. Are learned directly from the agent by trial and error over the real world. And one of the most interesting things about LLMs in the background of our discussion would be whether they actually have the ability to learn world models correctly. It's actually nowhere near settled, but most of the papers are essentially showing that they don't really have good world models. That's actually part of the reason why they don't do planning correctly, as we'll show in a minute. So can LLMs do planning? At the beginning, I was basically thinking, this is not even a question I need to worry about because they're essentially a system one, like an external system one for the entire humanity. Unlike system two, system one, they don't have a system two component. But lots of people were saying that they can do planning. And so the question then is, I tried to check too. This is actually, I've done this 1.5 years back. This is the more recent one with GPT-4o. I just said, by the way, in planning, AI planning literature, we think in terms of stacking blocks. That's the fruit fly of the planning problems. So if a block C is on top of block A and block B is separately on table, can you tell me how I can make a stack of blocks with block A on top of block B and block B on top of block C, but without moving block C? If you think about it, even though it's after lunch, you know that this problem can't actually be solved because you have to move C. But do LLMs say that? No, this is a very small problem. Notice what GPT-4o is doing. It is hallucinating the specification, it's hallucinating the physics, it's hallucinating the goal. In general, LLMs are amazingly gracious, polite apologizers until you correct their plan. Okay? So actually, I was saying this to New York Times when they were writing something about GPT-4o. Now you might say, well, that's just one problem, Rao, and you're being mean. What about the state-of-the-art things? In fact, much of my first part is going to show that essentially state-of-art planning, the LLMs, all fail pretty badly on even simple blocks world types of problems in terms of the correctness of the plan. And it turns out that these problems, the one that we tested on, They're not even unsolvable ones. They're all solvable ones. If you actually give unsolvable instances to LLMs, they do even worse. Okay? So this is basically what the current state of the art is. This is June 2024. So why do we think they do planning? Because we tend to confuse memory with reasoning. If you know the answer and you blurt it out, I don't know whether you just retrieved the answer or whether you went from the first principles. Showing that you didn't go from first principles, it actually requires a diagonalization argument, and that's oftentimes not all that easy to do. So I'll actually show you one diagonalization argument that we do for planning. The other things, of course, is they might be doing approximate reasoning. They might be approximating reasoning with pattern finding. In general, for example, if you're trying to get them to guess whether a random satisfiability instance is satisfiable, are they going to learn the Davis-Putnam procedure? Or are they more likely to learn the phase transition phenomenon? It turns out they're more likely to learn the phase transition phenomenon than the Davis-Putnam procedure. If you're interested in that, there's more of that on the side, but there's a nice paper by Guy van den Broek in Ichikai 23, which talks about the paradox of learning to reason. The other thing generally is LLMs are great at style, and they're not good for correctness. Their generative AI in general tries to learn properties of the distribution. They're learning the distribution. Saying we learn the distribution and also saying we'll be correct at an instance level are not actually making sense together as claims. And so you want to keep that in mind. So correctness and factuality is an instance level property, and LLMs are not actually good at doing it. Style is a population property, and LLMs are actually much better at doing it. And this is what we will leverage when we're using LLMs. Civilizationally, we always thought that style is harder than content. And so we tend to be impressed by style rather than the content. But now in the context of LLMs, style is easy. Content or correctness is actually harder. And that's what was remembering. And in general, one of my probably the most useful contributions to the AI literature is this copied version of XKCD cartoon, basically saying the impressive reasoning abilities of LLMs all depend on prompter actually knowing the answer. And in some sense, it becomes clear as I show you the examples. And so since I'm saying negative things about LLMs and I don't get the startup money, I made a t-shirt and I'm wearing that. So maybe I'll sell them after the fact. Okay, so again, as I said, LLMs have these limitations as well as they can be used in LLM modular frameworks. And then I have papers on that, we'll get to that. So that gets us to part 2, where basically I want to show you that LLMs actually can't plan, some of the literature about that. So, a while back, I think 1.5 years, 2 years back, we actually looked at GPT-3 and GPT-3.5 on block solved problems. It did very badly. And so we wrote something called LLMs can't plan. And that's become like surprising because most people think they can. And then GPT-4 came along and it has sparks. So the question is whether sparks of intelligence can make it solve planning problems. So this actually is a NeurIPS paper in December last year, which basically where we did a systematic evaluation of different ways of prompting the LLMs, GPT-4, with planning problems and basically checking, not the humans, but a verifier outside checks whether the plan is correct or not. Okay, the plan generation results have improved a little bit. So 34% from 5-6% from GPT-3. So that looks as if from GPT-3.5 to GPT-4, you already went to 34. By GPT-10, it'll be 170% accuracy. And that's what we all expect from AGI. So the question I had was, are LLMs retrieving based on the names, the facts that they have block-solved, and they have seen enough block-solved stuff on the web, or are they actually reasoning? Okay? Remember, memory versus reasoning. How do you tell? Well, it turns out we in planning community have a thing called planning competition, and back in 1998, Drew McDermott, who sadly passed away 2 years back, actually was worried that people might be writing domain-specific planners rather than a general planner that can handle any domain. And so by just looking at the names. So he came up with this idea called mystery domains, where you essentially translate the words into some random other words. So we did the same thing for LLMs. So for example, for blocks world, instead of picking up a block, we say attack an object. Unstack a block from top of another block, we say feast object from another object. Now you might say, well, this makes it very hard, but remember that the planning problem itself, the dynamics of the planning problem don't change just because you change the names of the predicates. This is like a 101 of logic, okay? And so the question is, if you really are doing reasoning rather than retrieving, you shouldn't have any trouble. And let me tell you that every random classical planner, the ones that people make fun of, they can solve both these domains equally well. They have no problem, okay? On the other hand, LLMs die. They just basically go from 34 to basically 0.16 kind of percentages, okay? And so, in fact, when this came out, I basically said, well, if people are worried about GPT-4 killing everybody, don't worry, just give it a blocks world problem, it'll get stuck, and then we can, survive to see another day. If you are surprised that, if you're at all surprised about this, let me tell you that there are other people who are realizing this too. This is one of the papers that I like, is by Tom Griffith's group, which basically is a different thing, where basically he just points out that what you tend to think is reasoning is oftentimes approximate retrieval. So basically, when I showed you the previous case, the fact that its performance worsened significantly just by changing names makes you realize that it was really doing retrieval, not reasoning effectively. So the question is, this Embers of Auto-Regression paper essentially looks at the fact that GPT-4 tends to do well on cipher, Caesar cipher decoding. This was one of the things that Sebastian Bubeck said is a spark of intelligence. And they questioned this by saying, Caesar cipher decoding is basically shifting letters by an offset, right? And they checked to see how it does for every possible offset. So the Caesar cipher can actually work for 2 offset, 5 offset, 9 offsets, all the way up to 25 offset, right? It turns out it does extremely well for offset 13 and very badly everywhere else. Those of you who are old enough know that Unix has a command called rot13, rotation by 13. That was the normal way we used to quote unquote cipher text, our plain text files, okay? And there's enough training data on that in the web scale corpora, whereas it's just not there for any other numbers. So it did not learn the procedure. It learned essentially how to convert a reasoning problem into a retrieval problem. Shouldn't be surprising. Okay, now mystery blocks world, coming back to it, if you ask LLMs, give the mystery blocks world domain to that and say, which of the domains does it remind you of? What is it most analogous to? Surprisingly enough, it tends to come with reasonably correct answer, like it's blocks world. So part of it actually knows that there's an analogy, but the other part doesn't know how to use that. So when people say he doesn't know that what his right hand is doing, his left hand doesn't know what his right hand is doing, LLMs don't know that they have 2 hands to begin with. They can answer each of these things, but they don't necessarily combine them. So in fact, we actually give this mapping directly to the LLM, the one that it gave, and it still does badly in terms of actually solving the problem. One last thing, because this ICML and because there are enough people who are already probably feeling that I'm being mean to LLMs, why are you making it solve blocks world with the names changed? And the usual way people tend to push back on LLMs can't do something is, but humans can't do it too. First of all, I don't understand this point, okay, because we do want things that machines should be able to do things more than what humans can do. They should do what humans do, but they can also do more than what humans do. And the second thing is, while it is the case that the humans have trouble with mystery blocks world compared to the blocks world, if you give them money, they will solve it. So we actually did, graduate students will solve any damn thing, man. So you can actually get people and say, look, this is the domain, and here is the rules, and then can you put together actions such that the goal is solved? And it turns out they actually will solve the problem correctly, okay? 100% correct. We tried to give money to LLM. Sam Altman was richer, but it was not doing any better, okay? So in general, while we slide by with a system 1, we do have a system 2. And we tend to use it when our life depends on it or we are getting free money, okay? Whereas LLMs don't have a system to, specifically speaking. That's the point. So that's the paper, actually. There's information on that, and there's a plan benchmark about it in New RIPS. That benchmark, people are trying it, still not going any further. As I can show you, as I showed you, the 2023 is ancient history. The latest LLMs do just as badly. This is Claude 3.5, Claude 3, GPT-4o, GPT-4, GPT-4 Turbo, Gemini, and Llama. In fact, some of these are specifically said that they do reasoning better, they do planning better. So what exactly are they saying they can do better? Okay, now you might say, well, of the prompting strategies, did you use chain of thought prompting? Chain of thought is actually a religion to some extent. People would like to say that if you give some examples on how the example is solved, LLM learns from it. Now, I'm an old AI guy. I know that advice taking is a hard situation. So, in fact, McCarthy, who is one of the founding fathers of AI, has actually said the whole point of one of his holy grails is advice taker program. Because advice taking involves operationalizing a high-level advice to a specific situation. And it's not easy at all. Unless, in fact, the advice is very tailor-made to this specific problem and nothing else. And so I basically will show you that chain of thought prompting essentially requires you to give advice that's very specifically tailored to that particular problem. There's no generalization that's going on. To give that, what we did was we took these Bloxwell problems, right? You can have four setups. Setup one, domain-independent chain of thought, where essentially we show it how, irrespective of the domain, if it has a plan, it can check whether the plan is correct by looking at the model and doing progression or regression. We just write it down, so the way you can write it to a graduate student. Setup two is very Bloxwell specific. We just expect that the goal is always a single stack, and the initial state can have multiple stacks of blocks. It turns out that in Block's world, you can always solve problems in optimal way by taking the initial state, put all the blocks on the table, and then construct them in the order they are appearing in the goal state. If you do this, you will at most be twice the optimal length, but at least you'll be correct. Okay, so we did that. Setup 3 specializes setup 2 by actually putting all the blocks on the table to begin with. And setup 4 not only does all the above, but makes the final stack be always lexicographically ordered. Always lexicographically ordered. So if it is A1 to A100, those blocks are appearing A1 to A100. So the smaller numbers are appearing on the top of the stack. So we give examples, let's say for 3 or 4 blocks problems about how to do this chain of thought for each of these setups. And without fail, they fail to generalize. They do better at the 3 and 4 blocks. And then as you can see from these pictures, the accuracy just degenerates as the number of blocks increase. Even as you were hearing me, you understood the procedure I told you about how to take the initial state, put all the blocks on the table and just put them up in the right order. That's the general procedure. Chain of thought is not allowing LLM to come up with learn the general procedure. That's exactly what is going on here. You might think that this is something crazy about Block's world. The real stuff LLMs can do might not have this problem. It turns out chain of thought's failure to generalize goes beyond planning. In fact, this is one of the examples of us doing Ersage natural science, where we stop as soon as we get good results and not look at how far they actually go. So if you take something like last letter concatenation, which is actually a thing they bring up in the chain of thought, original chain of thought paper, and you increase the number of words such that you have to do last letter concatenation, and you give the same chain of thought advice, the accuracy falls as the number of words increases. All of you understood last letter concatenation the moment I said last letter concatenation. You didn't care about, tell me how to do last letter concatenation for 4 words, for 5 words, for 10 words, for 15 words. If I have to do that, I will fire you as my graduate student, right? But LLMs actually, you have to do that. Now, you might be thinking that I'm making this whole thing up. Dale Schurmans, who is one of the co-authors of Chain of Thought paper, original chain of thought paper with tons and tons of citations, gave a keynote talk at ICAPS this year, and he basically said, I was right. Whatever we were saying is right. In fact, somebody tweeted that he said Rob was right, and my only comment was Rob is still right because nothing has changed. Chain of thought still seems to not generalize currently. React style prompting is another variation. We have a paper basically showing it doesn't work. Either in particular, they make this whole thing about think tags, and it turns out it doesn't matter where you put the think tags. If you put all of them in the front as well as in specific places, there's no difference in the performance. Furthermore, you need very, very task-specific chain of thought examples for it to actually have any improvement. And there's details in the paper, but essentially the same problem that they need something where the reasoning can be converted into pattern matching. And so you have to give very, very specific kind of knowledge, not a general procedure, okay? What if we fine-tuned LLMs with successful plans in the domain? Everybody does that, okay? Turns out they don't do that well for fine-tuning. But I want you to also think about what are you trying to achieve when you fine-tune? If basically fine-tuning converts reasoning into a retrieval problem, you're essentially calling, taking a huge number of problems, calling a classical planner, making it solve it, and then giving them all to the LLM so that it will get retrained on those so that its guesses are slightly better. Okay? But unless it generalizes, there is not going to be any, it's not worth the trouble you are taking. Sometimes you might be able to amortize. Most of the time, fine-tuning actually is not amortizable. Right now, we are going through a phase where the amount of money the companies are spending in fine-tuning, nobody is questioning it. Someday, it matters. Then the good old computer science will come into play and they'll say, is the cost that you're spending in the pre-training, is it being made up, amortized over the time you're using it, okay? In general, people tend to talk about LLMs in machine learning people, like obviously in versus outer distribution. But the point is, in versus outer distribution is irrelevant. What you really want to say when you can say that you want to reason is, are you able to get to the deductive closure of the facts that have been given to the LLM? Those of you who know logic know that deductive closure is all the theorems that you can prove given the base facts. And that's a pretty hard thing. That's what reasoning is. And what LLMs can do essentially is you give enough of the deductive closure as part of the training such that they will retrieve it back. There's actually a paper by another group which sort of shows the same thing, that LLMs basically will have trouble even doing in a graph where saying A is property 1 to B and B is property 2 to C. You want to be able to say that A is property 1, property 2 to C. It's a sort of a transitive closure, which is a poor man's version of deductive closure. And they say LLMs, other transformers, can't learn that either. Okay, this is the Ohio State group, I believe Watson's group. So inverse outer distribution is less relevant than deductive closure and whether or not you're able to capture the deductive closure. One other variation of this, if you don't want to give up on fine-tuning, is fine-tuning with derivational traces. In fact, one of these papers is actually appearing in Colm, Conference on Language Modeling. And I actually think that the paper doesn't make too much sense. Basically, what they're saying is, instead of just giving the problem and the solution, you give the problem and the trace, that the search tree and the solution, and then hope that LLM will complete both the trace and the solution. And they try to make some arguments that it actually improves performance. Unfortunately, actually, the trace that LLM generates doesn't correspond to any actual problem solving. It is guessing both the trace and the solution. And it turns out, if you were to look at it carefully, it has the same problems fine-tuning will have. So here's a paper that you can write, because this is coming up in Colm, and you can try to show that probably could be, might be explained in a different way. Okay. So can LLM self-critique? It turns out that, as I said, self-critiquing arguments assume that somehow LLMs, the critiquing part, the verification is cheaper than generation, and so maybe LLMs can do that better. Okay, that's gobbledygook. As I said, actually, it's reasoning, and it's not the complexity of reasoning is not what makes LLMs fail. Last letter concatenation, exactly how hard is that problem? And yet they fail as the number of words increase. So we looked at 3 different reasoning domains: game of 24, graph coloring, and planning. Game of 24 you already heard about, which is coming up with numbers with arithmetic operations such that the answer would be 24. Okay, and graph coloring is making sure that adjacent vertices are not given the same color. Planning is the same kind of planning problems. And so we considered an LLM guessing the solution, an LLM guessing the solution and going in a loop to check whether the solution is correct, and if it's not correct, sending itself back prompting, saying correct the coloring. Okay? And then we compared it to also an external verifier, which actually knows what is correct coloring, what is correct solution, etc. And you'll notice that when you look at this, LLM self-critiquing actually a mirage. It turns out that when they try to correct their own solutions, they oftentimes worsen their performance than just guessing it up front. And this is what I was saying, that if you don't know what you're doing, you're better off not questioning your guesses. Okay? Because what happens is when they correct their solutions, they hallucinate. They assume that there are errors in the solution that aren't there, and they'll miss the errors in the solution that are actually there. And they keep telling themselves to keep changing the solution such that this particular back prompt will work. And so they wind up becoming worse than actually what they're supposed to be. So it basically is the false negatives and false positives in the correctness critiquing that actually kill them. Okay, fine-tuning, one way you can improve is to actually separately train an LLM to just do better at verification. We did this and there are some promising results, but out of the box, a pre-trained LLM is no better at verification than it is at generation. And in fact, if you make it verify, it actually can worsen the performance. Now, this might make you think, why are people writing all these papers about LLMs, self-reflection, self-verification, etc., etc.? In general, it's partly because it's like the blind man and the elephant. They're looking at different aspects of the issue. So in particular, a lot of these problems, a lot of the problems used in papers talking about how self-reflection improves are on tasks such as improving an essay. These are tacit knowledge tasks. There's no formal verifier to check whether one essay is better than the other essay. Okay? And in those cases, there is no formal verifier. And so whatever LLM does, you're hoping that the humans seem to be thinking they're happy. And so this is a big issue. Whereas when there are formal verifications, such as game of 24, blocks fold, constraint satisfaction, they actually seem to do quite badly. Okay, there's actually other people who have come up with the similar conclusions now, but I think the tide is turning in terms of whether or not they can do self-verification, but that's the reality. And the other thing that you might want to remember is sometimes verification might be possible because the training data contains not only correct data, but also corrections data. There's actually a great example of some work which actually did GitHub differences and then use the differences with the meta heuristic that whenever you change the file from one version to another version, maybe the second version is better. And so you kind of correct it. And so you use that, you will have a slightly better advantage in doing the verification than you are in doing the generation. So those are some of the possible reasons why that might be happening. In general, it's this whole style versus content issue. LLMs are great at style, and they're bad at content or correctness. So if you want to use style, and we are writing, my whole point is I want to use LLMs for what they're good at. So there's another Colm paper from my group that's showing up in, basically that shows how to look at LLM behavior and and look at the style of their behavior and criticize it. So for example, the behavior might actually be achieving the goal, but some implicit constraints are possibly violated. So for example, if you ask me to give a pair of scissors, and if I give this pair of scissors to you, I have achieved the goal. But if I gave the pair of scissors to you with the sticky end, the pointy end pointing towards you, especially if I'm a robot, you'll probably run for the hills because this robot is coming up to you with pointy scissors. So that's the style consideration, unless you want to make into a correctness explicit constraint. And these are the kinds of things that you can improve by critiquing. LLMs actually do a fairly reasonable job on that sort of style criticisms. Okay, so all of this basically is to say that autoregressive LLMs don't necessarily seem to have reasoning capability, and this should not be particularly surprising. This is, by the way, the stump talk of Jan LeCun, where we seem to have one of his slides is basically about our old paper on LLM still can't plan. He keeps continuing to show that. Okay. On the other hand, literature seems full of papers saying they can do this. They can slice, they can dice, and they can do. And who am I to question NeurIPS reviewers? Which, by the way, are you guys? You are the reviewers of NeurIPS. And so I'm hoping that you will know how to check these papers. Okay. So this, as to why people are still writing these papers, corresponds to what I was telling you about planning and the different aspects of planning in the beginning of the talk. In general, planning as used in common parlance involves two pieces: planning knowledge, actions, preconditions, and effects, for example, general recipes, old examples such as case libraries and so on, and plan generation and verification techniques. That is, the thing that you guessed is actually correct with respect to some model, either internal or given model of the world. The old AI planners used to focus mostly on the second one, and they're actually good at it. LLMs are better at the first part, not on the second part. They just cannot do combinatorics. They can guess models, they can guess plans, they can guess case libraries because they've been trained on the huge, web scale corpora. The point is they can't guarantee, they cannot give me any kind of guarantees that the plan they come up with is actually correct. Okay? So how am I making this up? So it turns out that you can actually check this. Okay? So you can go to Bloxworld and you can make sure that actions will not interact with each other. So it becomes a basically very easy ergodic domain where all actions, none of them have preconditions and none of them delete anybody's preconditions. So you can, if you have 5 goals, you can essentially do 5 actions for 5 goals. Okay? If you do this, so if you do precondition relaxation as well as delete relaxation, and if you do both of them, the green part, which is the percentage of correct plans, increases. Do you see what I'm saying? However, it's still there is red because LLMs are actually lousy at counting the number of goals that they have to support, so they might have forgotten to actually support some goals. But it does make the point that if you reduce the interactions between the actions, you can essentially convert planning into more of a retrieval problem because you can retrieve a sub-plan for each of the sub-goal and just splash them together any which way and it will work. The problem with planning in general is any which way won't work. You have to look at combinatorially and see which version actually works. That's the usual problem in planning as well as RL. So why are LLMs being trumpeted as doing planning? Well, it's because they assume they either work in domains where there are no interactions or they're mostly ergodic, as I told you in the beginning of the talk. And so it turns out that almost planning is not needed there. And that's where planning actually works in general because they don't have to guarantee that the plan works correctly. Okay, most of the time they will guess a plan and the human in the loop, if in fact there are interactions, human in the loop is supposed to make sure that those things are taken care of. If it is easy for you, good for you. If not, just don't give the credit to the LLM saying it gave a correct plan that can be executed. So that's the point I'm trying to make. In general, approximate retrieval of plans is not planning. It's only part of the planning. You still need to make sure that the pieces that you retrieved actually work together correctly. That's what planning and scheduling is all about. Okay? So, in fact, if you go to React, inner monologue, event tree of thought, the kind of examples they look at tend to be very ergodic planning domains where you can almost blunder on until you hit the right solution because you can never get stuck, okay? And if you're playing with simulators, this is a given because simulator can always be reset. And so it becomes easier. And so it's worthwhile keeping that in mind. There's a beautiful example of this last year that, I don't know, some of you are probably from US and you know this guy, Rick Steves, who writes travel books. I got one of them for Vienna, right? And people were buying travel books, not by Rick Steves, but the ones that basically was generated by ChatGPT. Okay, and they have nice pictures and they have some reasonable-ish, travel plan, and people were buying it because that's like $10 cheaper than the Rick Steves book. And then they'll come to Vienna, they'll come to Florence, and they'll find that some logistics information, such as this museum is not open on Tuesdays, or that you're supposed to have called ahead to get the ticket, actually winds up being critical. And so they basically hated those books, even though they look nice, they look like travel plans, but they're not travel plans. And so they all returned those books. And the New York Times had a nice article pointing this out. And so that's actually a telling example of what happens when you do LLMs to generate plans. You can generate wedding plans, just don't get married with them. So if you want to argue with your friend that LLMs can plan, I'll tell you both ways, right? That's the way to kind of argue. But at least you know what you're doing. If you want to argue that LLMs can plan, pick a domain with very high branching factor of unenumerated actions, like MacGyver planning, where interactions are very low or nobody cares. Their LLMs actually look like they're doing planning. If on the other hand, you want to argue with your friend that LLMs can't plan, then pick a domain with a few enumerated action, which looks like actually a simpler case, but the action interactions are non-trivial, such as the blocks work, where I told you all the actions, and yet you can't actually put the correct sequence together. So both of these are true because LLMs are good at guessing, but not good at reasoning. Okay, now this actually brings up this other related issue, which is back prompting by humans. Sometimes, multiple, at least the Twitter world, and maybe partly, probably in papers too, people give credit to LLMs because they say, it came up with a plan and I found this error, I said it's error, and then it corrected it. Well, you found the error. LLM didn't find the error. Okay, so this is clever hands phenomenon at work, and you should make sure it's fine if it's one of those computer-supported cooperative works where it is easy for you to check what's wrong with the plan, and you want LLM to come up with the guesses, but don't say that LLM is doing all the work. That's a very reasonable point to make, okay? In fact, oftentimes these things are made up of these various kinds of prompting techniques, chain of thought, tree of thought, and so I wrote this paper, a made-up abstract for April 1st, called Forest of Jumbled Thoughts Prompting, an ultra-general way to use LLMs for solving, planning, reasoning, world peace, and climate change tasks. And in fact, it has beautiful sentences. I am tickled myself at that abstract. You should read it. We say, for example, one of the lines is, we prove by reduction to Rube Goldberg machines that the Forest of Jumbled Thought Prompting eventually makes LLM solve any problem for which the prompting graduate students know the answer, because they'll keep pestering it until LLM gives the correct answer and say it gave the correct answer, okay? This is obviously tongue-in-cheek. Funny part is more people asked me for the full paper on this than the other papers that I'm writing. But that's also true about the current world. The one other thing that people keep talking about is LLMs actually do have the correct plan in the top K, and I already told you, top K doesn't mean a thing if it is actually ergodic. By the way, it turns out that if you have a big set of true-false questions, right, I have top 2 answers for every true-false question. It's either true or false, and I'll generate both of them, and you pick the right one. That's nonsensical. That's not actually solving the problem. And in particular, in the case of non-ergodic domains, who is picking the correct plan? And the person or the thing that picks the correct plan should know the domain dynamics. Otherwise, it's going to be bad. Okay? So that's something that you want to understand, that answer in the top K plans is not enough of a way out of it. One last thing before this part is, doesn't Copilot for code, all of you know Copilot for code? Code seems to be more general than plans. You're generating programs, right? So the fact that everybody swears by Copilot for code, doesn't that mean that Rav is just kind of unnecessarily complaining because they can actually do the problems harder than planning, which is just generating automatic code? Well, we know that's not the case. Basically, Copilot works with humans in the loop. Most of the time, the pieces of the code that they generate are the ones that are very common. It's just not common for you, and enough people have written enough of it, so that the thing that you had to go to Stack Exchange for before is the stuff that LLMs can do, which is good for you. There's nothing wrong with it. But don't say that LLMs are doing automatic programming, because automatic programming is AGI. When that happens, I'm very impressed. The only sane people who are doing LLMs with automatic programming actually use LLMs to generate code and check it using unit tests, which is the LLM Modular, which I'll be talking about next. That's pretty much the only way to make sure. If not, you are the verifier. You are checking the guess that it's giving and checking whether that code is correct. And which is why every once in a while on Twitter, people will say, I just spent 4 hours trying to debug this really bad bug that was introduced in a 15-line code that Copilot came up with. Because it just gives it looks like a pretty reasonable piece of code, but it's not actually checked. All of this should make you worry about agentic LLMs and when they cannot be used. Acting versus planning is two very different things. Calling a function doesn't make it planning. Okay, you can actually, the most horrible example I can think of is if you have a toddler in your home and you have guns lying around, the toddler will use the gun, not necessarily for the right reasons. Okay, doing actions and making sure that the actions that you take will satisfy good, desirable outcomes is basically, that's the second part, is planning. Just doing the action is just affordances. Okay, so in particular, there's a significant misunderstanding about the fact that, because it can call functions, then it must be able to do planning. What if the functions you're calling will wind up having interactions? If you can't solve blocks world, I can write blocks world planning as a bunch of function calls and you will still fail. And you want to keep that in mind. So LLMs themselves cannot be expected to plan unless you have some verifier outside, or you don't mind that the plan doesn't kill the world. Like the kind of thing that CrowdStrike did last couple of days, where you call a little software thing, but it basically brings the world down. That is something that's very much possible because LLMs are not guaranteeing the plan's correctness that they are generating. Okay, so that's second part. The third part is some sane roles for LLMs in planning. This is the positive part, which I kind of been hinting at, and I want to end it with that. So the sane roles is LLMs can play multiple roles in supporting planning, even though they can't generate plans and give guarantees that they're correct. Somebody else who knows better can be a verifier, for example, they can be useful. In general, by the way, LLMs are great idea generators. How many of you know how Einstein came up with E equal to mc squared? It so happens, I was there when this Far Side cartoon points out that he was trying E equal to mc cube, mc power 5, mc power 7, and this janitor lady came, cleaned the table and said, now it's all squared away, it's all squared away. Then he got the idea. Okay, you might laugh, but in general, if you ask any mathematician, where did they get their breakthrough ideas? They almost never say, we were working very hard at our table and the idea came. It's either they're in the toilet, they're walking in some forest or something and the idea came. Ideas can come anywhere. There is such a thing as being lost and not having ideas. But having an idea given to you doesn't make it a correct idea. Fermat basically had an idea, and Andrew Weil spent 17 years proving that that idea is correct. Okay? You need both. And LLMs are great for the first, but you need somebody who can verify that the idea is correct. That's very useful. So in general, in the good old GoFi, you would have this kind of, the way of doing AI systems would be, you will go and talk to experts, domain experts, and then subject matter experts, the human will do this, write them all in some logical format, and then give it to some logical reasoning, etc. And this was called the knowledge engineering bottleneck, because it's very painful to talk to experts by these humans. They will have jobs, but it's like not a great way to say. The interesting thing is that's bad. LLM just sort of automated that whole part of it. LLMs can actually give you domain models, rules, etc., approximately. And then you need to make sure that they are actually making sense with some verifier, either human or automated verifiers in the loop. Okay? Again, this is not coming out of thin air. In fact, the funny part is in AI, of late, if you have a single problem and you go ask a specific person, how do I solve this problem? And they write some bunch of rules, that's cheating. If on the other hand, before you do this, you train an LLM on the entire human knowledge as has been exported onto the web, then you solve your problem. That's modern AI, because you don't seem to care about the pre-training cost, hopefully assuming that it will be amortized for a period of time. So that's how LLMs are actually able to do this. So in general, planning in the age of LLMs should take into account the fact that the domain models can be guessed by LLMs. In fact, of all the people, some of you are probably into deep reinforcement learning, and I make these jokes to my grad students that in one area where you can always show improvement is deep reinforcement learning, because the underlying approaches are so darned inefficient that pretty much anything will improve the performance. Okay, why? Because they tend to go with the lowest level formal model of the domain, such as like almost atomic level domain models. LLMs can actually guess approximate domain models that can be used in context of RL to actually do much better. I'll show you a paper that came in ICML 2022, which actually uses approximately incorrect models to improve deep reinforcement learners. And if there's one thing LLMs are good at, coming up with approximately correct anything is what they're good at. Where there are no guarantees, but they might actually be useful. So, and of course, LLMs can assist human planners. We have already talked about this. If it helps you, the ideas it's giving is helping you, who am I to question? It improved computer-supported cooperative work. You can use LLMs as heuristics for sound planners. So they can give action heuristics or plan heuristics, but the planner then takes that and goes forward with that. So one of the earliest things we did was we would actually ask LLM to come up with a plan and then give it to a classical, normal first principles planner that tries to modify that solution until all the errors in that solution are gone. This is a local search planner. And it turns out that it's good for both, because LLM is actually good at giving ideas that are not guaranteed. And this planner gets a plan which may be possibly likely to be desirable to humans, because remember, LLMs are better at style, and then they can make sure that the plan actually works. So this is something that we could show will actually improving performance. It's in the new Reeves paper. Now it turns out this is something connected to what used to be called case-based planning, where essentially in the old days, you would have a bunch of old plans, and given a new problem, you look at one of these plans in the library and check if you can modify it such that you can solve the new problem. LLM is essentially representing this case base in a sort of n-gram way, and it's generating the potentially relevant case on demand, and then you are correcting it. That's what I was doing. So, in fact, you can do LLM plus RAG if you're interested in retrieval augmented generation, where the RAG has more desirable plans for your own little domain, and then this would be a way in which you can actually let the LLM come up as a heuristic. In fact, one of the earliest papers on saying that LLMs can be useful for planning is SayCan, which was basically using Google's PaLM system, and they used LLM as a heuristic. Okay, it picks possible actions that can be done. They actually have a deep reinforcement learning system, and that checks which actions are actually doable in the current scenario, and then they take the intersection and try to do them. That's what SayCan does. And so it's essentially LLM is only suggesting actions, and you taking the intersection of it with the actions that actually can be done. Okay, so that's the way to win. In general, I find that this type of work can all be thought of as sort of something that I made up called LLM Modular Frameworks, where there's a large language model that plays multiple roles in planning, and on the top level, what it's happening is it generates a guess. And there's a bank of critiques, bank of verifiers, some of which are style critiques, some of which are correctness critiques. They're all suggesting fixes or saying this plan is correct. And these then are sent as a back prompt to the LLM, which will then come up with a new solution. Okay, and if you see a lot of work that's being done, it essentially almost falls in this unifying framework. And this is basically what I'm giving a position paper tomorrow, but I'll talk to you a little bit about it here too, because it actually talks about other people's work also as a unifying framework here. So in general, the summary of it is that LLM Modular is a generate test framework with LLMs generating candidate plans and critiques testing those plans. Okay, and the LLMs play a variety of constructive roles here. They can generate candidate plans. They can be an approximate source of models driving the correctness critiques. So correctness critiques will require a domain model. You can tease out the domain model for from LLM, the knowledge engineering task, except knowledge engineering task now is cheaper because LLM is coming up with something more reasonable. This is like a co-pilot for domain models. Okay, they can certainly act as style critiques, and they can help collate the criticism from all the critics in this meta controller, which tries to pool all these things and send a combined back prompt to the LLM. And then help with format change. Of course, they can, if different critiques use different formal representations, they can automatically help in converting the representation. Again, none of this is guaranteed, but because it's a generate test framework, and the only thing that comes out is something that correctness critiques have said is correct, that's your guarantee, that you would not send out a plan that won't work. Completeness is a different matter, I'll talk about in a minute. So one thing about LLM Modular is I'm pushing for, I think it's useful to have critiques rather than full solvers interfacing with LLMs. Because a critique can actually be a constructive critique, so it can be a solver that solves a relaxed plan and uses that plan as a back prompt. But in general, if you stick to a solver and then just make it a single unidirectional thing from LLM to the solver, you get stuck with the expressiveness constraints of the solver. And in general, solvers are not particularly efficient. I mean, we do have this stuff, but they're not very efficient yet. And so LLMs basically generating solutions and in this generate test framework actually works. One thing that many of you who may have done intro to AI might be thinking generate test is the dumbest idea, right? Because you do generate test before you do anything else, like even A-star search, right? Why is it any better with LLMs? Well, generate test would be better if generator has a higher density of generating solutions that are more likely to be correct. And to some extent, it's an empirical observation. LLMs at least will generate solutions that have a higher style. And stylistically, they look like Bloxworld plans. Stylistically, they look like wedding plans. And so there's a higher density, hopefully. And so that's part of the reason why LLM Modular would work. In fact, we took the bare bones versions of LLM Modular with just one single critique and used it in Bloxworld, right? And it turns out that just with one single Bloxworld critique, which checks the plan, and instead of LLM critiquing it, it's this Bloxworld critique, which uses the PDDL domain model and a VAL system, which can soundly check whether the plan is correct with respect to the model. Such systems exist in any domain. So if you do that, with 15 iterations going back and forth between the verifier and the LLM, the performance, the accuracy increases to 82%. Furthermore, it's very impressive because the 82% of the time when it gives a plan, it is correct. When it doesn't give a plan, it will never give a plan that's actually incorrect because critique would not let the incorrect plan go. So 82% of the time you actually spoke up and you did have a correct solution. The rest of the time you didn't speak up, and that's pretty good. Okay, this is basically how robust planning would work. Okay, again, as I said, we should prefer verifiers to solvers. Solver is basically verifier plus search, and the generate test already has a poor form of search, and so you might as well use the generate from the LLM and then the verifier outside. Okay, now the bank of critiques, I do want to talk a little bit more about them, that you can have different kinds of critiques, correctness critiques and style critiques. And as I mentioned, that behavior criticism, that's a style critique. Correctness critique is the plan actually achieving the goals and are all the actions working correctly? There are no interactions, etc. The correctness critiques are the ones that LLMs can't do. That's basically what our work is showing. Style criticism, there is no competition. So basically, whatever LLMs do is the best you have going, because there is really, does anybody know a formal way of checking how good an essay is? There's no such thing, right? That's the tacit knowledge task. Okay, so LLMs can be directly used for critiquing style, but for the correctness, you actually use external verifiers, which might be using models which themselves can be teased out from the LLMs. That's actually the point that I was making. Critiques can be binary, such as try again. They can be constructive. They can say, here is the errors in the candidate, here's a variation. Why don't you try this version for this part of the problem? And so that actually is a useful thing. If you can provide, critics can do relaxed solving and give a relaxed plan, which then LLM incorporates in the back prompting, okay? They can also be partial, which is basically, they don't give a guarantee that the plan works, but they can at least make sure that it doesn't have some of the obvious errors. This is basically what we do with software. Unit tests are what you do with software. And if you pass all the unit tests, if you fail a unit test, you definitely are a bad program. If you pass all the unit tests, that's what CrowdStrike did. They passed all the unit tests, I hope, for their own good. And yet, it basically brought down the world, okay? So unit testing is actually what, the LLM-based automatic programming systems currently are using. And that's a kind of a partial criticism, okay? And by the way, to be able to do unit testing, one of the things that I forgot to mention with respect to the code is one thing that Copilot has that general planning doesn't is, of all the things, Python interpreter. If you give an arbitrary program to Python interpreter, it will give you what the output of that program would be. That is actually an amazing achievement of human civilization. LLMs didn't write Python interpreters, thank goodness, okay? But it is actually a model for a particular language, how to actually get the semantic import of that thing. That doesn't exist for natural language. That's the whole point. That's why programming languages are formal. Natural language is a lot more general, and there is no single interpreter. And in general, for any arbitrary world, there may not be any interpreter checking unless you have simulators for that world. So Python interpreter is actually a simulator for the Python program. Okay, oh my God, okay. Let's see. Yeah, let me just make sure that I won't kill my thing, but let's see. So the other thing is, if there's a, I actually have it. The other thing, thank you very much. The other thing is that the meta controller combines the criticisms from the various critiques and sends it back as a prompt. And as part of that, it can actually do what is important, something that people don't realize, called prompt diversification, which is that LLMs may not actually be able to generate all possible relevant candidates. In fact, there's a great work by Vaishnav Nagarajan that you guys should look at. He basically points out, in ICML, he points out that a transformer model trained because of the teacher force training will actually not be able to even retrieve the data that's been trained on. So the incompleteness in the generation. So, however, you can improve you can make it more complete by sending prompt diversification strategies. One idea would be, for the plan, in this branch, give me the plans that start with action A1. In this branch, do with action A2. In this branch, do action A3. If you see what I'm saying, that's basically tree of thoughts, which basically sort of tries to simulate the search by diversifying the prompts. In general, it is relevant to see that soundness and completeness of LLM modulo. Soundness comes from the critiques, the correctness critiques being correct. Completeness, on the other hand, as I said, it's not guaranteed that it would actually be generating all possible relevant solutions such that one of them will actually be correct. And this where the prompt diversification strategies help. And the prompt diversification strategies can be used from search techniques, basically, because that's actually a model of the world, because you do know that every plan has to work with one of these actions, and so you're telling the actions that it needs to start with. Okay, so that's actually looking at tree of thoughts in this light, not the way they wrote. And in fact, there's a long Twitter thread that I wrote, but basically you realize that what tree of thoughts is doing is prompt diversification so that LLM winds up generating more and more candidates, at least one of which is correct. To actually point this out, we did the following thing, that ignore entire apparatus of tree of thoughts, just ask LLM to generate 150 solutions for, let's say, a 24 puzzle, and then check if any one of them is correct by an external verifier, and you basically come very close to tree of thought performance. So what is really working there is prompt diversification so that you generate candidates are from different parts of the space. And to actually diversify correctly, you need to know something about the domain that LLM itself is not directly using. So that's something that you want to keep. So as I said, LLMs can be used as style critiques for the behavior. We also have an HRI paper showing that they can be used as a resident human that kind of gives whether humans looking at this behavior or the plan, would they be happy? So this is sort of mental modeling. And it's not guaranteed to be always correct, but it actually does better than just coming up with a plan that might be surprising to the humans. So LLMs can be used as a human proxies, where being seen as a better plan by the humans is a style rather than the correctness criterion. And I already showed you the LLM behavior part. Okay. Then format change is something that everybody and their brother wants to use for LLMs, but I think that's sort of a little too unambitious. They're extremely good at format change anyway. You want to do it more than that. So if you do want to do format change, you can essentially, like 3-4 years back, we essentially used GPT-3 to look at textual plans on the web and convert them to PDDL specifications so that then formal planners can reason with them. There is a cottage industry of that kind of a work before individual papers converting in NLP community, individual papers for converting a textual procedure into a formal procedure. LLMs do much better than any of those bespoke approaches already. Okay, and there are other approaches such as AutoTamp, for example. All it does is it takes a specification, converts it into a formal language that a formal solver can use. Okay, in general, that's a single directional interface. LLM just converts natural language to a formal specification, and then there is a solver that uses that formal specification to solve the problem. There's nothing wrong with it, but I think we can do a lot more interesting stuff with LLMs, because if you understood what I said in the beginning of the talk, LLMs are actually great at this MacGyver kind of planning where they actually can come up with better, more actions in particular, and they can actually be using, generating candidates which can be verified by the external verifiers rather than getting stuck with the expressiveness limitations of the solvers themselves. There's another paper called LLM plus P, which actually does the same thing but for PDL domains. Again, these are single directional ones. One interesting thing about LLM plus P is as part of their work, they actually show that everything we have claiming is actually true, that LLMs cannot actually solve the planning problems. And then they say, we will just do it by converting the natural language specification into PDL problem specification so that you can use the PDL solver to solve it. All I'm saying is you can do much better with a band of critiques because you can use style criticisms. You can also use different kinds of expressiveness constraints in the verifiers. One other thing that people are into is synthetic data that LLM generates to train itself. It boggles my mind that if LLMs are not actually generating correct plans, and if you make them generate a lot more correct plans that may be incorrect and then fine-tune them on them, will they become better? No, they won't become better, because that's like noise being used to train you, incorrect data being used to train you. But on the other hand, normally the way the synthetic data people wind up doing is they actually use an external solver to solve the problem and then pre-train. That's what I was showing you as Llama cartoon earlier. With LLM Modular, actually, you can actually generate the plans with some guarantees, because the critics are saying they're correct plans. And then if you have enough of those plans, you can then actually use them for fine-tuning. And that would be a better way of generating synthetic data than depending on somebody else's solver. Okay, the last thing that I want to mention here is the critiques, some of the correctness critiques will need domain models to work. In the work, the first things, the results that I showed, I gave the domain model in PDDL myself, my students did. But we wrote a paper in NeurIPS, which basically shows that LLMs are good at guessing anything. They can guess plans, they can also get domain models. They can also get programs, for example, right? So when you can guess domain models and you have, with a semi-automated way, to actually have a sort of an LLM modular approach for improving the domain model, with a human itself as one of the verifiers, okay? That will actually reduce the amount of time taken for coming up with the domain, which then once you get the domain, it will run the verifier. And this is a paper in NeurIPS which actually talks about this particular way of using LLMs for coming up with the domain models. In general, the interesting point that I mentioned earlier is LLMs are actually deep reinforcement learning systems in particular can really benefit from approximately correct domain models because the simulator can actually check whether or not the plan is working. So the idea generation is where they're getting stuck at. So LLMs can generate domain models and you can do analysis on those domain models. For example, this paper in ICML 2022 basically took a handwritten approximate domain model and does high-level analysis such as landmarks, and the deep reinforcement learning system actually tries to go through all the landmarks to get to the goal, and it improves the performance quite significantly. And now with LLMs in the loop, you can actually have that automated. By the way, code as hierarchical policies kind of papers can actually be understood in this form because they're actually good at guessing but without any guarantees. One last thing is there is a travel planning benchmark that somebody else, there's a whole bunch of planning benchmark papers that have come up after ours. One of which is this travel planning benchmark that's from the Ohio State group. And it's actually, as I said, travel planning is a kind of a scheduling-ish problem because you essentially pick a bunch of activities and make sure that the constraints are not going to be violated. They basically came up with this benchmark and showed that GPT-4 does 0.6% accuracy. 0.6%. You are thinking that Rao made up this blocks world just to kill LLMs. Travel planning that you apparently would like to do, if you care about actual constraints, such as actually making sure that you don't take non-existent flights and expect that you will somehow miraculously come to Vienna. So in those kinds of cases, travel planning, so basically LLMs are generating plans that are only 0.6% of the time correct with respect to hard constraints. And we applied this sort of LLM modulo ideas where basically different set of critiques for each type of constraints and let the LLM generate guesses which are then improved. And with just not too much work, we could just improve it by 10%. I think 6 times or better accuracy. Where we get stuck right now is actually the diversification of the travel plans has to be improved because LLMs generator can get into loops and they basically generate very similar kinds of candidates. Okay, that's pretty much what Tree of Thoughts was getting out of by using classical search. And to do classical search, you need some domain model of the domain. LLMs didn't tell you the domain model. That's something that you want to remember. Okay, so this is the results on travel benchmark, and this is actually on the archive too. Now, one last thing before I leave this is, I kind of did this strange thing. In the whole bunch of the first part, I said LLMs are not actually good for planning. And then I said they can still be used for planning in this LLM modular way. So you can ask a reasonable question for somebody like me that, are you trying to just get some LLM papers? Kind of. After you wouldn't have called me to do this tutorial if I didn't do LLM. If I said how to do right PDDL planning, none of you would care. You want to care about LLM planning. But more seriously, I really believe that LLM modulo actually is best for both LLMs and the first principle solvers. Because the first principle solvers tended to be picking the language or the expressiveness with respect to which they can give guarantees. And if the user comes and says, here's my problem, it's their responsibility to make sure that the problem constraints are satisfied by the expressiveness restrictions of the solver. That's a dumb way to have any customers. Customer is always right. You let the customer give the problem and do as well as you can. Okay, for example, real world planning, such as NASA, when it sends mission planning, etc. It's not that they can completely guarantee, they guarantee with respect to a partial model of the world, and that just reduces at least obvious failures, just like unit tests do, okay? And what LLM Modular allows you to do is essentially not get stuck with a predefined expressiveness restrictions of the underlying solver, but LLMs can generate, as I said, stochastic plans, plans with stochastic dynamics, plans with partial observability, plans with multi-agents, all of them they just generate happily with no guarantees. They're just as bad for single agents as they are for multiple agents. But then, because they can generate this, and if you have a large number of composable critiques, you can actually do a better job of solving harder problems for which actually solvers don't really exist. So that's basically the way I would think LLM Modular makes sense. Most of you probably won't know, but at one point of time, knowledge representation community would say, we will only look at knowledge representation languages that are tractable. And if they're not tractable, we won't take that problem. But most of the knowledge representation problems deal with knowledge that is actually not in the tractable class. And so they would say, that's not our problem, we are not going to deal with it. And these two guys, John Doyle and Ramesh Patil, once wrote this thing called Two Theses of Knowledge Representation, arguing that customer is always right. You do the best you can with respect to the problem that the customer has, rather than saying, I'll only work with this particular representation limitations. It is from that perspective, for a few of you who might be coming from formal modeling, formal solver perspectives, LLM Modular is actually a worthwhile thing to do, not just to get extra LLM papers. To recap, in many of the frameworks that's use LLMs, external verifiers play a central role for ensuring soundness. LLMs are idea generators without guaranteed correctness. Different prompting strategies help increase the chance of sampling workable solutions, including this prompt diversification part. And it's a sort of a unifying view that kind of summarizes the constructive roles that LLMs can play, and also includes a minimum set of components that ensure correctness of the output, such as correctness critics, sound correctness critics. That gets me to the very end, which is the summary, that I want you to remember a few things at least. It's been a long 2 hours with one single speaker speaking in his inimitable accent. So I want you to at least go back to this slide and make sure that you understand what planning is, especially if you're not from planning, and so that you can see whether the claim you are making is about planning or scheduling, and whether or not it is about ergodic domains, and whether or not it's about models that are given by outsiders versus models that you learn. In the case of tree of thoughts, they wind up using a model that the people write to actually prompt diversify. So it's not that the LLM comes up with the model that directly prompt diversifies, because if it does that, it's not guaranteed typically, okay? And then I also mentioned that these LLMs cannot do a whole bunch of things in autonomous modes, and it's worthwhile being skeptical. Even if you don't completely believe everything I said, at least be a little more skeptical about claims about chain of thought works, self-verification works, etc., etc. Just a little more skepticism. But then don't be too negative, because actually they're very useful. They're actually very good idea generators, and idea generators of all kinds of things, including planning, domain models, etc., etc. And LLM Modular is a way of thinking about how to put them all together to actually make the LLMs work that way. And that's the thing that I showed. And then the very last thing, and I'll give some time for questions if there are any, is if you do want to argue that LLMs can't plan, pick a domain with high branching factor of unenumerated actions where the interactions are low, where actually planning is not even needed. There's a beautiful quote associated with Gibbon, who says, teaching is only effective in those fortuitous circumstances where the student almost doesn't need to be taught. LLMs are great at planning in the domains where planning doesn't have to be done. okay, in the sense of actually combinatorial interactions. They're just coming up with the ideas. They're not guaranteeing correctness, but it turns out that there's high density of reasonably correct solutions everywhere, and you don't get stuck. And so that's where you'll say LLMs do planning. But if you take something like travel planning and actually put constraints, LLMs die. Constraints that you actually care about. And similarly, if you want to argue that LLMs cannot plan, pick a domain, a simpler domain with few enumerated actions, but the action interactions are non-trivial, and you do have to give guarantees. It turns out that the more general case is essentially unenumerated actions, and you're still providing guarantees. That's harder than both of these, and LLMs will die there too, for sure. It's just that in a bigger case, you can split into two pieces, and I'm telling you which piece they die and which piece they don't. And I believe that ends my thing. And tomorrow, if you don't get time to ask me any more questions right now, tomorrow I'll be standing in front of this poster, and you can come and ask me more questions there. And thank you very much for your patience after lunch. Thank you.
Thank you very much. Thank you very much for your talk. Are there any questions in the room?
Yes, go ahead.
Hi, that was a great talk.
Thank you.
I have a question. So, we at Turing.com work with most foundational LLM companies, OpenAI, Anthropic, Google, Meta, and the others on human data for SFT, RLHF, and so on, for coding, debugging, and other things. Agentic workflows are, of course, very interesting, and while we have made quite a bit of progress on function calling and related areas, I do think planning is quite crucial. So suppose you had a team of, say, 50 software developers, 50 other knowledge workers, and you could produce human data to make the models better at general planning. How would you design a task?
So you're basically asking me, I think, in terms of what I discussed here, you're asking me, how can I fine tune such that I can convert reasoning into retrieval? Okay, it depends very much on knowing the distribution, the very specific distribution of the questions that are going to come, and then making sure that you provide the correct data for that. In general, that's a reasonable thing. You can basically, I think a lot of people are doing it. For example, if you have a domain for which in the web scale data, your domain is not well represented, giving extra information about that in fine tuning will at least improve the performance of LLM. But it doesn't generalize. Even the notion of generalization we have, which is you get the procedure, they can't do, and it should not be surprising. Okay? Anything else?
Hi, I have two questions.
Yeah. Right.
The first question is that, around more than 100 years back, Hilbert and Alfred Tarski asked the notion of truth, basically question what is truth, right? And Tarski came up with this model theory in...
Sorry, I can't hear you clearly. I hope you guys heard me better than I'm able to hear you. Otherwise, yeah, go ahead.
So, more than 100 years back, David Hilbert and Alfred Tarski asked what is truth? What is truth, right? And in response, Tarski came up with the notion of what is called model theory, what we call model theory in logic, right? So do you think that today, what is happening is that that these LLMs lack a model theory, a first-order model, for example, first-order logic model, right, that can say that, okay, this is true, this sentences are true in this model, and this sentences are not true. So is that the case here? Second question I have is that, if you see the theory of abstract interpretation, classic theory of abstract interpretation by Patrick Cuso and Radhia Cuso, where there is predicate abstraction. Predicate abstraction is that you give predicates and then the predicate abstraction system comes up with a model. And it can come up with a model in the abstract domain, not in the concrete domain, because the abstract domain has less details than the concrete domain, right? So is it possible that we can use such a similar technique in the with LLMs, because in an abstract domain where you have much less details, right, an LLM might work better? So there are two questions.
Okay, so yeah, so with respect to the first question, in general, I think what I would say is, from a logic perspective, if you give a set of base facts, if I say A and A implies B, is the system able to then say that B will be true? That's one part of entailment. Interestingly, LLMs can't even do a single step. That's what that grokking paper that I mentioned was saying. But what happens, the reason people are impressed is LLMs are not trained just on base facts. They're trained both on base facts and some part of the deductive closure. Interestingly enough, this other paper that I was talking about, they say that only when you throw stuff from the transitive closure does it then convert the reasoning into a pattern finding problem. So ultimately, I'm not saying, we are not necessarily going back to these philosophical issues of what is truth. It's just mostly to make sure that the egregious problems that you can avoid are stopped. That's what human civilization has always been. None of the plans that we make in real world are guaranteed correct. But having a partial model of the world and checking whether the plan works with respect to that is like a unit test, right? And if it fails the unit test, it definitely is a bad program. If it passes it, it may still be a bad program. So that's one way of handling the LLM, the issue of truth business. With respect to the other thing, I didn't completely catch all the questions. We should talk offline. But in general, think of LLMs as I mentioned earlier, think of LLMs as an external, non-veridical memory for humanity as a whole. So it's a system one, not just for you, but a system one for the entire humanity. Okay, and they are great at generating ideas with higher density of potentially stuff that is relevant with, that's representative in the web scale corpora, but there's no guarantee that the idea they come up with is correct. And there is a difference. And so you can basically use any idea which can use a system one and then do a verification or builds on top. So in fact, one of the things we are doing in LLM Modular is make the LLM first come up with hierarchical plans and then ask it to improve. This basically is work on this in planning, but you're asking, instead of just saying generate the plan for the entire, guess the entire plan, you're saying first give me the plan which is correct with respect to the kind of cities I'll visit. Then I will ask you, what are the constraints and so on. When you do this, you are imposing what you think is a good abstraction on top of LLMs. There's nothing wrong with that as long as you don't delude yourself that LLM did it all. Okay? Yes? I think, you need some mic somewhere, I guess. Okay, go ahead. And then maybe after her, yeah.
Okay. Hi, thanks for the awesome tutorial. I think you talked a lot about how to use today's LLMs the right way for planning, right? Like using them as idea generators and so on. But if you had to give an opinion or your perspective on how to train next-gen LLMs to be system to reasoners and thinkers, I'm curious, what would you say? Like, does that make sense? Like, we didn't talk at all about what can we do for improving next-gen LLMs, and I'm curious if...
Next generation LLMs, okay.
Yes.
So this is actually a very good question. Let's just get it clear. In my sense is, I'm not saying that AI systems cannot reason. I'm only saying that LLMs, which are a very, very specific kind of AI system. It's an auto-regressive n-gram model. That's what every possible LLM has been. If you just keep making them bigger and bigger, all you're going to be able to do is convert reasoning into retrieval at best. Okay? If you're talking about generating, and so what I was telling you is, you could use the LLMs that exist right now and increase guarantees of reasoning by combining the other formal methods with LLMs. There are other people, for example, such as Yann LeCun, for example, he's excited about what he calls Japanese architecture. I call it Japanese architecture. He calls it Japa architecture, that somehow he will train it in such a way that the model itself will be better in terms of, so from the initial planning slides, one of the questions is getting the agent to have an internal model. In fact, one of the very interesting things is we do guess a solution and are able to correct it ourselves. We actually do very good self-verification. This is why people thought LLMs can do it too. But we are not LLMs, I'm sorry to say. Okay, right? And LLMs, on the other hand, we actually have a pretty good model of the world, and we might just use a system one to guess the solution, but then if required, we will check our solution with respect to our system 2 model. LLMs doesn't have that capability. You see what I'm saying? And so they minimum require some good way of learning internal models. That's one possible longer term way. And I'm telling you, as of now, there are actual techniques that actually exist that can take LLMs to farther down, as they basically off the shelf. Yes.
So you mentioned that LLMs don't have a system 2 model within them, but these models are pretty huge and have a lot of parameters, right? And a lot of knowledge in them. So why wouldn't they be able to do system 2 reasoning by themselves? Like, I know that they can't, but shouldn't they be able to?
No, so basically that's what this entire tutorial is. We can talk a lot more, but in general, they're not basically doing what you think you are doing, which is I have the general procedure, I can guess the solution, I can check if the solution is correct with respect to the procedure. They can't do that. They do not have that capability. You can, however, make their guesses be higher density correct by just fine-tuning the heck out. Okay, but that didn't make them do reasoning. It just made them fake reasoning by converting reasoning into retrieval. There's nothing wrong with that. In fact, one of the things that I keep saying is people are very surprised that GPT-4 will solve every standardized exam, right? And that the GREs and SATs, they can do better than you guys. But really, one thing about standardized exams is every standardized exam has a standardized question bank. And we depend on humans not to actually have another life so that they won't look at the entire standardized question bank all over the internet before going to the exam. Most of you guys, when you go to your Microsoft interview, etc., do this already. But in general, basically, fine-tuning will convert reasoning into retrieval. And so it becomes, it's from practical perspective, it's okay. But it just will always fail because I can always come up with these, diagonalization arguments, such as the example that I gave about, changing the names, etc. That basically show that you're actually memorizing rather than reasoning. One other thing that I mentioned, I think I mentioned this, that I keep telling people that, there's this interview question called, why are manhole covers round? The very first time Microsoft asked that question, somebody had to actually use system 2. Now, nobody uses system 2 to answer the damn question because they all prepare for the interviews. It's become part of, this is the question, this is the answer. And of course, because you are human, you want to make sure that the interviewer thinks you're doing reasoning, you will pause for a while and then blurt out the answer. Funnily enough, there's actually papers in LLMs which say, make them pause, maybe they will reason better, which is as silly as it gets. The unfortunate reality of this whole area now, is very silly ideas are getting through the reviewing because you guys are reviewing it and you don't actually know what planning is, what reasoning is, and you're thinking it's similar to other stuff that's being published. So the half-life period for many of these papers is going to be extremely low. Yes.
So just...
no, I think we have to take next one.
Thank you. I think we have time for only one last question.
Thank you for the tutorial. It was really, really good. So my question is, when you think about language model as a probabilistic model, right? So it is generating multiple of these diverse answers. So say if there is no formal verification approach, so can we look at the distributional statistics of the generated samples, say looking at a semantic similarity or something to say which has more probability to be correct?
So that's basically, I made this sort of binary distinction between style and correctness, but I also mentioned, again, this is afternoon and I said lots of things that we hear 8 times, with better acoustics, you will get my point. But even though I made this distinction between style and correctness, you can sometimes convert style into a correctness requirement, okay? Or rather correctness into a style requirement, okay? Because LLMs are good at style, okay? This is basically related to a whole bunch of ideas called constrained decoding approaches for LLMs, where, in fact, Marvin Minsky, I don't know, I hope some of you remember that name. Marvin Minsky basically said all of intelligence is taking the test part of generate test and putting it into generate. Okay, so if you increase the density of better solutions, you are better off. And one way of doing that essentially is fine-tuning. Another way is constrained decoding. But all of them increase the density. There's still no guarantees. Okay, thank you.
Okay, thank you very much. This is the end of this tutorial. So let's give Subhao a big round of applause for the session.
Thank you.
Thank you.